Now let's take a look at what it means to measure color using an image sensor. We know that color has to do with the wavelength of light. So let's assume that the incoming flux from a particular point in the scene is P of lambda, which is a photon flux as a function of wavelength. That photon flux arrives at your silicon pixel, and the pixel converts it into electron flux I. And the quantum efficiency of the material that you use to convert photons to electrons is defined as the ratio of the electron flux generated by the material to the photon flux that is incident on the material for a given wavelength of light. So the quantum efficiency is a function of wavelength. It's called Q of lambda. So let's take a look at what the quantum efficiency is for silicon. So in this case of silicon, when you go to high wavelengths, remember that visible light is between 400 nanometers and 700 nanometers. Now, when you go to somewhere around 1,000 nanometers, it turns out that the silicon's quantum efficiency is 1. It's almost perfect, meaning to say that every photon that it receives of that wavelength gets converted to an electron. But this quantum efficiency begins to fall as you go down in wavelength, and somewhere around 400 nanometers, it drops to almost 0. So one can say that silicon is virtually transparent for wavelengths above 1,000 or so nanometers, and it gets almost opaque for wavelengths below 400 nanometers. So now let's take a look at what happens when you have a single wavelength of light. That's lambda is equal to lambda I. This is called monochromatic light. And let's say that the flux is P lambda I. So we know from the definition of quantum efficiency that the electron flux I is equal to Q lambda I, P lambda I. But now we know that for any point in the scene, you have a range of wavelengths coming from it, that it reflects light with photon flux, which varies as a function of lambda. This is called a spectral distribution, P lambda. So in this case, what is the electron flux going to be? Well, let's take a look at a narrow band of wavelengths, which goes from lambda to lambda plus d lambda. So in this case, the flux that's arriving at the pixel is P lambda d lambda. And if you want to find the electron flux generated by the pixel for the entire spectral distribution, it's nothing but Q lambda, P lambda, D lambda integrated from 0 to infinity. That's the total number of electrons that you're going to get for the incoming light. So now the question is, if I give you I, which is the electron flux, you of course know the quantum efficiency Q of lambda. Can you tell me what P of lambda is? This function P of lambda, the spectral distribution. Well, the answer is no, because there are many P lambdas that I can multiply with Q lambda to get the same I. So how do we measure P of lambda? Well, we use filters. So in front of your pixel, you're going to place a filter Fi of lambda. And then the question is, what filter should you use to get all of P lambda? Well, what we can do is use a filter which is a narrow band. That is, make sure that Fi lambda is a delta function positioned as lambda I. What is a delta function? It's infinitesimally thin and infinitely tall, but it has an area equal to 1. That's a delta function for you right here. Delta lambda minus lambda I is a delta function centered at lambda I. So now what do you get? You get I equal to Q lambda, P lambda, Fi lambda, D lambda integral. And we know that Fi lambda is delta lambda minus lambda I. It's a delta function. And what this gives you is the value of Q lambda, P lambda at lambda I. This is called the sifting property of a delta function. It basically picks out that value wherever it's centered of the rest of the function. So you get Q lambda I, P lambda I is equal to I. So you're able to read out the value of P lambda at lambda I. And now the question is, how many filters do you need to recover all of P lambda? Well, at first glance, you would say an infinite number of filters. But it turns out that you don't need an infinite number of filters. If P lambda is a smooth function, we will see later in our image processing lectures that you can use a smaller number of measurements to recover P lambda without losing any information. So now, that brings us to the topic of color. What is color? It turns out that color is not a physical quantity that you measure. It is human response to different wavelengths of light. So, as I mentioned earlier, the visible light spectrum, the light that is visible to us, lies between 400 nanometers, which is bluish, velvetish, to 700 nanometers, which is red. Anything that is lower than 400 nanometers or right next to 400 nanometers is called ultraviolet light. We cannot see it. And anything that's beyond red, 700 nanometers, is infrared light. Again, we can't see it. Now, this actually brings up an interesting point, which is we can design cameras to measure information in the ultraviolet spectrum or infrared spectrum as well. In other words, we can design computer vision systems that go well beyond the visible light spectrum and therefore are able to perceive things that you and I simply cannot perceive. That's one of the advantages of using computer vision. It allows us to walk into visual worlds right next to our visual world, but cannot be perceived by us. So that's the visible light spectrum. And so now the question is, do we humans actually recover the spectral distribution P of lambda within the visible light spectrum for any given point? Well, it turns out the human eye, the sensor of the human eye, which is the retina, has two types of pixels, rods and cones. And the rods are not really sensitive to the color of light. They're just looking for the brightness of the incoming light. The cones are sensitive to color, and there are essentially three types of cones. These are neurochemical sensors that respond to three types of color, so to speak. So let's take a look at these rods and cones. So here you have the human eye. We've seen this before. You have your cornea, you have your lens, and the lens forms an image on the retina, which is sitting back here. And the retina, like I said earlier, also does a little bit of early processing, but this is where all your pixels are sitting. So let's take a look at the architecture, if you will, of the retina. You see that you have your rods and cones, or your pixels right here. And then this information goes into bipolar cells, which are sitting right here. And that goes into ganglion cells right here. So there's a little bit of visual processing, early visual processing happening. And then that image, that semi-processed image, is passed through the optic nerve to the visual cortex in the brain. So question for you, where is light coming from? Which direction is light coming from in this diagram? Well, you would assume that if the pixels are sitting here, light really should be coming from the bottom. It turns out that's not the case. Light is actually coming from the top and passing through the ganglion and bipolar cells to get to your rods and cones. Interesting fact, not exactly sure why nature decided to design the retina that way. Now let's come back to the rods and cones. So this is a scanning electron microscope image of rods and cones. You can see that the rods actually look like rods. They're cylindrical, more or less. And the cones look like cones, and that's why they're called so, right here. And they essentially do the same thing. They take light in, and they're able to generate an activation, an impulse that goes off to the brain. However, they respond to different types of light, so to speak. So they have different proteins. Rods have rhodopsin as a protein, and cones have photopsin as the protein. And so rods are able to measure what I would call black and whitish images. They come into effect particularly when you're walking out in darkness, when there's very little light, say moonlight, say for instance. You may have noticed that you're not able to actually discern the colors of things in the scene. You just know whether there's light or no light. So you get a very dim image, which is colorless. The cones, when there's plenty of light, are able to discern the colors of various things in the scene. And so vision using rods is called scotopic vision, and vision using cones is called photopic vision. These are two different modes that the eye operates in. And once they measure something in terms of photon flux, they send this as nerve impulses down the optic nerve for further processing. So now, let's take a look at the distribution of cones particularly. Let's set aside rods for a minute. You have essentially three types of cones: red cones, green cones, and blue cones. We call them these because they respond to reddish light, greenish light, and bluish light, and you see their spatial distribution on the retina, and it turns out that they are maximally, most dense, they have maximum resolution in the fovea, which is the place where you have maximum acuity. When you look at something in the scene, that something is falling on the fovea and everything else is peripheral vision. So that's where you have maximum number of rods and cones. In terms of relative numbers of rods and cones, you have roughly 120 million rods versus only about 7 million cones on the retina. And most of your cones, like I said, are in the foveal region right here. Very high density and then falling off very fast. And then when it comes to the rods, you have almost no rods in the center of the fovea, and then you have lots of rods, very high density, and then the resolution begins to fall off as you go to the periphery of the field of view. And right here, you see that you don't have any rods or cones. Any idea what that is? Well, that's the blind spot. That's where the image goes through the optic nerve back to the brain, and that's a place where you don't have any rods and cones in the eye. Now, you must be wondering, why is it that you're not seeing your blind spot all the time? It turns out that your brain is filling in visual information in that region. And so we believe we have an absolutely continuous image, but it actually has a hole in it, as we'll see shortly. So now let's talk about the spectral response. Just like we talked about the quantum efficiency of silicon, we can talk about the spectral responses of the cones, the three types of cones. So the spectral responses are called the tri-stimulus curves. So think about these as exactly like the quantum efficiency of silicon, but these are the quantum efficiencies of the red, green, and blue cones. And so you have HB lambda, HG lambda, and HR lambda. And so now, what do these cones measure? Well, very much as in the case of our silicon pixel, you have HR lambda, P lambda. P lambda, again, is a spectral distribution of the incoming light. The integral of that gives you one number, R. Similarly, you get G, and you get B. So you get these three numbers corresponding to any incoming spectral distribution. You don't get the complete spectral distribution. So we see here that the eye does not measure the complete spectral distribution P of lambda. It basically gives you three numbers corresponding to any P of lambda. And so that brings us back to the old problem, which is that there are multiple P lambdas. There's an entire continuum of P lambdas that actually generate the same RGB values. And these are called metamers. So here you're seeing different P lambdas, significantly different P lambdas, which actually produce the same RGB values in the eye. And in fact, the values that they produce are roughly 115, 60, and 108. And the color that we perceive is this color here, which is purplish, purple or violet, or whatever that color is, magenta perhaps. That's the color we perceive for all of these spectral distributions. So the existence of these metamers is telling you that there's a lot of spectral distributions that exist in the world which are very different from one another, which we humans perceive to be the same color. So that brings us to Young's experiment on mixing colors. So what Young found out is that you can take three wavelengths of light, just 3 wavelengths, specific wavelengths of light, and you can mix them. In this case, he's using a different projector for each wavelength of light, and you can see that wherever the projected circles overlap, you're getting these different colors. And it turns out that just with these 3 wavelengths, you can actually reproduce the sensation of virtually all the colors that you and I are able to see. And so these 3 wavelengths are 650, 530, and 410 nanometers. Now, of course, you can change these wavelengths and you would get very similar effects, but 3 wavelengths of light are enough to produce virtually all the colors that you and I are able to perceive. And this is why cameras and displays have red, green, and blue filters on them. So let's take a look at how we can capture a color image. So one way to do this is by using what's called the dichroic prism. This prism is a fairly sophisticated piece of optics, and when you show it an image, that image gets split into 3 components: a reddish image, a bluish image, and a greenish image. And so now what you can do is you can place a sensor on these 3 faces that you're seeing right here of this dichroic prism, and this sensor would capture a red image, a green image, and this one would capture a blue image. The images are not red, green, and blue. They're capturing those wavelengths of light. And they're perfectly aligned. So you can now stack these 3 images and you essentially have red, green, and blue values at each pixel. So that's one way to do it, albeit a little bit bulky and a little bit advanced in terms of requiring alignment and precision and so on. It would be nice to be able to measure color using a single chip, just one sensor. And that's what's usually done, at least in consumer cameras. And that's done using what's called a color mosaic. So in this case, again, you see pixels, but you have different color filters in front of each pixel. These are the red pixels, and these are the green pixels, and the blue pixels. So any given pixel only measures one particular color, and so at any location in the image, you're only measuring one color, but you know that you have neighbors that measure the other colors. And so the basic idea is you take an image which has red, green, and blue values as shown here. So each pixel is either red, green, and blue. And then you use interpolation, which is a technique we'll talk about later, to reconstruct the full red, green, blue image, the color image. So in other words, if you measured blue at this point, you then say, given my neighbors, my red and green neighbors, what red and green values would I have measured at this point if I had a green pixel there and a red pixel there? So you end up with your color image. This process of interpolating this color mosaic image to get a full color image is called demosaicing.